C# and AI Masterclass by Edgar Milvus Volume 8, Chapter 2. Now, let's explore Chapter 2, Configuring the Kernel, Azure OpenAI vs. Ollama. Let's discuss theoretical foundations. The theoretical foundation of configuring the semantic kernel hinges on the principle of abstraction. In AI engineering, we rarely interact with a large language model, LLM, directly via raw HTTP requests. Instead, we interact with an abstraction layer that standardizes the chaos of disparate AI providers into a predictable, programmable interface. This subsection establishes the architectural philosophy required to decouple your application's core logic from the specific AI service provider, enabling seamless transitions between high-scale cloud services like Azure OpenAI and local, privacy-centric models like Ollama. Now, let's explore the abstraction of the AI service. At its core, the semantic kernel is an orchestration engine. It does not inherently know how to generate text, it delegates this responsibility to a service connector. In C#, this is modeled using interfaces. The most critical interface in this context is iChat completion service. Imagine a translator in a high-stakes diplomatic negotiation. The diplomat, your application logic, delivers a speech. The translator, the AI service, converts that speech into a language the listener, the LLM, understands. The diplomat does not care if the translator is using a human, a sophisticated software, or a dictionary. The diplomat only cares that the message is delivered and understood. The interface iChat completion service is the contract between the diplomat and the translator. It guarantees that GetChat message contents async will return a list of chat messages, regardless of whether the underlying implementation is calling an Azure endpoint or a local Ollama process. The real-world analogy, the universal remote. Consider a universal remote control. The buttons, power, volume up, input select, represent the methods defined in the interface. The remote does not care if it is pointing at a Sony TV, a Samsung TV, or a projector. The Sony TV implementation knows how to convert the power button press into an infrared signal specific to Sony, while the Samsung implementation converts the same button press into a different signal. By configuring the semantic kernel, you are essentially programming the universal remote to point at a specific device. Swapping from Azure OpenAI to Ollama is as simple as changing the battery pack, the service registration, without changing the buttons you press. Now, let's explore the kernel as a service container. The kernel instance in semantic kernel acts as a dependency injection, DI, container specifically tailored for AI orchestration. This builds directly upon the concept of the kernel instance introduced in Book 1, where we established the kernel as the central nervous system of our AI application. In traditional software engineering, the DI container manages the lifecycle of objects. In AI engineering, the kernel manages the lifecycle and configuration of intelligence sources. When we register a service, we are not merely storing an API key, we are defining a strategy for how the kernel resolves requests for intelligence. Azure OpenAI, the distributed cloud. This represents a stateless, high-availability service. The kernel configuration here involves endpoints, API keys, and versioning. It relies on the network. It is the serverless paradigm applied to intelligence. 2. Ollama, the localized edge. This represents a stateful, resource-constrained environment. The kernel configuration here involves local ports, model file names, and hardware acceleration, GPU/CPU. It relies on local resources. It is the embedded paradigm applied to intelligence. Turning our attention to the role of modern C# features in configuration. To manage this complexity efficiently, we utilize modern C# features, specifically records and configuration binding. Now, let's explore 1. Configuration records, immutability. In older C# versions, configuration was often stored in mutable classes or dictionaries, leading to runtime errors if a property was overwritten. In modern AI applications, we treat configuration as immutable data. Once the kernel is built, its configuration should be frozen to ensure deterministic behavior. Here at line 1, we import the system.component model namespace. This namespace provides classes that are used to implement the runtime and design time behavior of components and controls. In this specific context, it's likely being used for attributes like description attribute, which you'll see later. This is a standard practice for adding metadata to our code, making it more understandable and discoverable, especially in scenarios like toolkits or frameworks where components might be listed or described programmatically. Look at line 3 and 4. We're defining a record named Azure OpenAI config. Records, introduced in C number 9, are a fantastic choice for immutable data models. Notice how we declare deployment name, endpoint, and API key as positional parameters. This automatically generates a constructor, properties, and equals, get hash code, and toString methods, all optimized for immutability. This design choice is crucial for configuration objects because once the configuration is loaded, we generally don't want it to change accidentally. Immutability helps prevent subtle bugs that can arise from shared mutable state, making our application more robust and predictable. It also naturally supports thread safety, which is a significant advantage in concurrent environments. Similarly, at line 5, we define Ollama config, another record. Just like Azure OpenAI config, it uses positional parameters for model name and endpoint. This consistency in using records for configuration types is a good architectural pattern. It signals that these objects are primarily for holding data and are not intended to have complex behavior or mutable state. By inheriting from service config, we're establishing a common type that allows us to treat different service configurations polymorphically. This is a foundational step for building a flexible system that can swap out AI providers without extensive code changes, adhering to the open/closed principle. At lines 7 and 8, we define an abstract record called service config. The description, base class for service configuration, attribute, enabled by our system.component model import, provides a human-readable description for this type. This is particularly useful in development tools, reflection-based scenarios, or even for generating documentation. Making service config an abstract record means it cannot be instantiated directly. Its purpose is to serve as a base type, forcing derived classes, like Azure OpenAI config and Ollama config, to implement specific configuration details while guaranteeing they all share a common service config identity. This is a powerful abstraction for managing different AI service providers under a unified interface, promoting extensibility and maintainability in our AI engineering projects. Why this matters? If you pass a mutable configuration object to the kernel, and another thread modifies the API key or endpoint while the kernel is processing a request, you introduce race conditions. By using record types, we enforce immutability, ensuring that the translator does not change dialect halfway through the conversation. Now, let's explore 2. The adapter pattern via dependency injection. The kernel builder uses the adapter pattern to wrap external services. When you call .add Azure OpenAI chat completion, you are registering an adapter that translates the semantic kernel's internal prompt handling logic into the specific API contract of Azure OpenAI. The what if scenario: what if Azure OpenAI introduces a new v2024-08-01 preview API that changes the JSON structure of the response? If you had hard-coded HTTP calls throughout your application, you would have to refactor every call site. With the kernel configuration approach, you only update the adapter, the service connector. The rest of your application, which calls iChatCompletionService.getChatMessageContents remains untouched. Moving on to visualizing the configuration flow. The following diagram illustrates the flow of a request through the abstraction layers. Note how the kernel acts as a firewall between the application logic and the specific provider implementation. A request flows from the application logic through the kernel, acting as a firewall, before being routed to the specific provider implementation. Let's discuss deep dive, token management and latency implications. Configuration is not just about connectivity, it is about performance characteristics. When we configure the kernel, we implicitly accept the latency and token constraints of the underlying model. Token usage: in Azure OpenAI, token usage is a billing metric. The kernel configuration must be precise to avoid prompt injection costs. By using the prompt template engine, discussed in Book 3, we can optimize prompts before they reach the model. However, the choice of model, e.g., GPT-4 versus GPT-3.5 Turbo, dictates the token limit per request. The kernel must be aware of these limits to truncate or summarize context effectively. Latency, theoretical implication: when configuring the kernel for Ollama, we often enable streaming, get streaming chat message contents async, to provide a perceived faster response to the user, as the local model generates tokens sequentially. For Azure, we might use the same streaming approach to reduce time to first token, TTFT, but the network overhead remains a constant factor. Moving on to the why of configuration strategy. Testing in CI/CD. By abstracting the configuration, we can inject a mock service connector during unit testing. This allows us to test the logic of our AI agents without actually calling an expensive LLM or requiring a local Ollama instance. 2. Fallback strategies. Advanced configurations allow for circuit breaker patterns. If the Azure OpenAI service is down or throttled, the kernel configuration can be set up to automatically failover to a backup model, perhaps a smaller, locally hosted model via Ollama, to ensure the application remains functional. 3. Context awareness. The configuration defines the persona of the AI. By binding the kernel to specific execution settings, temperature, top, frequency penalty, we tune the probabilistic nature of the model. Azure and Ollama may interpret these parameters slightly differently, the abstraction layer normalizes them. Turning our attention to theoretical foundations. The theoretical foundation of this chapter is that intelligence in software is a pluggable resource. By leveraging C# interfaces and dependency injection, we treat the AI model not as a monolithic entity, but as a swappable component. This allows us to architect systems that are resilient to provider outages, cost-effective in development, and scalable in production. Whether the kernel is pointing to a cloud endpoint or a local process, the application's logic remains agnostic, focusing purely on the orchestration of thought rather than the mechanics of transmission. Now, let's explore basic code example. Here, we're bringing in the necessary components from the Microsoft Semantic Kernel library. Notice that we're importing specific connectors for OpenAI, both Azure and Standard, and Ollama. This modular approach allows us to easily swap out or add new AI providers without fundamentally changing our core application logic. The system.component model namespace is typically used for attributes like description, which we'll see later for defining plugin metadata. This is a common pattern for framework extensibility. These lines define constants for our AI service configurations. Observe how we're explicitly stating that in a real-world application, these sensitive credentials, like API keys and endpoints, should never be hard-coded. Instead, they should be loaded from secure sources like environment variables, Azure Key Vault, or appsettings.json. Hard-coding credentials is a significant security risk, especially when deploying to production, as it could expose sensitive access tokens. This separation of configuration from code is a fundamental best practice for secure and maintainable applications. We're introducing the kernel factory class, which employs the factory method design pattern. This pattern is crucial here because it abstracts the process of creating a kernel instance. The calling code doesn't need to know the intricate details of how to configure an Azure OpenAI service versus an Ollama service, it just asks the factory for a kernel. This promotes loose coupling and makes our application much more flexible. If we wanted to add support for Google Gemini or another LLM, we would simply add another create method to this factory without touching the main application logic. The create Azure OpenAI service method is our first concrete factory method. Inside create Azure OpenAI service, we first instantiate a kernel.createBuilder. This builder follows the builder design pattern, allowing us to construct a complex kernel object step by step. We then use builder.add Azure OpenAI chat completion to register our Azure OpenAI service. This is where we pass in the deployment name, endpoint, and API key constants we defined earlier. The builder internally uses dependency injection, DI, to manage these services. Finally, build assembles all the registered components into a ready-to-use kernel instance. This pattern is highly extensible. We could add more services like embedding generators or text-to-speech here if needed. Similarly, the create_Ollama service method demonstrates how easy it is to swap providers thanks to the factory pattern in semantic kernel's abstraction. We again use kernel.createBuilder, and then builder.add Ollama chat completion. Notice that Ollama typically runs locally and often doesn't require an API key, which simplifies its configuration. We provide the model ID, e.g., Llama 3.2, and the local endpoint. This highlights semantic kernel's flexibility in integrating with various types of LLM providers, from cloud-based services like Azure OpenAI to local open-source models via Ollama. The consistency in the builder pattern, add, chat completion, across different providers is a key architectural strength. Here, we define a simple C# class, timePlugin, which acts as a semantic kernel plugin. The kernel function, attribute is crucial, it marks the getCurrentTime method as a function that the AI can invoke. The description, attribute provides a human-readable explanation of what the function does. This description is vital because it's often used by the LLM during function calling to understand when and how to use the plugin. Without a clear description, the LLM might struggle to identify the plugin's purpose. This mechanism allows us to extend the AI's capabilities by providing it with access to external tools and data, a core concept in agentic AI. This section marks the beginning of our main application logic within the program class. Observe the comment at line 62, which reiterates the benefit of our kernel factory pattern, the ability to swap AI providers with minimal code changes. This is a powerful architectural advantage, allowing for experimentation with different LLMs, B-testing, or switching providers based on cost, performance, or availability without rewriting large portions of the application. The main method is asynchronous, async task main, because interacting with LLMs typically involves network calls and I/O operations that are best handled asynchronously to prevent blocking the main thread. We start by prompting the user to select an AI provider. This interactive choice demonstrates the flexibility of our setup. The choice trim == 2 conditional operator elegantly selects between create Ollama service and create Azure OpenAI service. In a production environment, this decision wouldn't be a user prompt but rather a configuration setting or a dynamic routing logic based on factors like workload, cost, or specific model capabilities. This selection mechanism is a direct benefit of using the kernel factory. After creating the kernel instance, we immediately import our time plugin into it using kernel.importPluginFromObject. We give it the name time. This step makes the getCurrentTime function available to the LLM. When the AI processes a prompt, it will now be aware of a tool named time with a function getCurrentTime that retrieves the current local time. This is a fundamental step in enabling function calling, also known as tool use or agent capabilities, within Semantic Kernel. The LLM can then decide if and when to invoke this function based on the user's prompt. We define our prompt and, critically, execution settings. The prompt, "What is the current time? Please use the time plugin," explicitly guides the AI to use the plugin. The OpenAI prompt execution settings are essential for configuring how the LLM behaves during execution. Specifically, toolCallBehavior.AutoInvoke kernel functions tells Semantic Kernel to automatically execute any function call suggested by the LLM. Without this setting, the kernel might just return the LLM suggestion to call a function, leaving the actual execution to the developer. Auto-invoke kernel functions streamlines the process, making the AI act as a more autonomous agent. This try-catch block handles the core interaction with the semantic kernel. Await kernel.invoke prompt async, prompt, execution settings, is where the magic happens. The kernel sends the prompt and execution settings to the configured LLM. If the LLM determines that a plugin function, like getCurrentTime, is needed, and auto-invoke kernel functions is enabled, the kernel will execute that function, feed its result back to the LLM, and then get the final, refined response. This iterative process of LLM-tool-call-LLM is the essence of agentic behavior. The catch block is a basic error handler. In a production system, we'd use robust logging frameworks like Serilog or Nlog to capture detailed error information and potentially notify monitoring systems. The error handling in this catch block is a basic but important safety net. In a real-world application, simply writing to the console isn't sufficient. We would integrate with a comprehensive logging solution, e.g., Application Insights, Elasticsearch, Splunk, to capture the full exception details, including stack traces, contextual information, and user IDs. This allows for effective debugging, monitoring of application health, and proactive identification of issues. Ignoring or poorly handling exceptions can lead to silent failures and a poor user experience, especially in AI applications where model responses can sometimes be unpredictable or lead to unexpected errors. Thank you for your attention. This lesson is excerpted from Volume 8, Chapter 2 of the C# and AI Masterclass ebook series and from the volume, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns. You can find all the details here. https://github.com/edgarmilvus/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.